Hello everyone, our next chapter is morphological image processing. Before discussing about various logical operations, we will first discuss what is a morphology. The word morphology commonly denotes a branch of biology that deals with the form and structure of animals and plants. In this, the same word is used in the context of mathematical morphology as a tool for extracting image components that are useful in the representation and description of region, shape such as boundaries, skeletons, and the convex hull. Here, I have defined two fundamental morphological operations, that is dilation and erosion, in terms of the union or intersection of an image with the translated shape called structuring element. First of all, what is dilation? Dilation is an operation that grows or thickens objects in an image. The specific manner and extent of this thickening is controlled by a shape referred to as a structuring element. Graphically, structuring elements can be represented either by a matrix of zeros and ones or as a set of foreground, that is one-valued pixels. Toolbox function imdilate performs dilation. Its basic calling syntax is a2 equals to imdilate a comma b. For the moment, the inputs and output are assumed to be binary, but the same syntax can deal with grayscale functions. Toolbox function strel constructs structuring elements with a variety of shapes and sizes. Its basic syntax is se equals to strel shape comma parameters, where shape is a string specifying the desired shape and parameters is a list of parameters that specify information about the shape such as its size. Next is erosion. Erosion shrinks or thins objects in a binary image. As in dilation, the manner and extent of shrinking is controlled by a structuring element. Erosion is performed by toolbox function imerode, whose syntax is se equals to strel shape comma parameters, then a2 equals to imerode a comma se. Next topic is combining dilation and erosion. In image processing applications, dilation and erosion are used most often in various combinations. An image will undergo a series of dilations or erosions using the same or sometimes different structuring elements. There are basically three of the most common combinations of dilation and erosion, such as opening, closing, and hit or miss transformation. Now we are going to start with opening and closing. Opening and closing are implemented by toolbox function IamOpen and IamClose. These functions have the syntax forms of C equals to IamOpen a comma b and C equals to IamClose a comma b, where A is a binary image and B is a matrix of zeros and ones that specifies the structuring element. Next is hit or miss transformation. It is useful to be able to match specified configurations of pixels in an image, such as isolated foreground pixels or pixels that are endpoints of line segments. The hit or miss transformation is useful for applications of these types. The hit or miss transformation is defined in terms of two structuring elements. It is implemented by toolbox function bw hitmiss, which has the following syntax as C equals to bw hitmiss a comma b1 comma b2, where C is the result, A is the input image, and b1 and b2 are the structuring elements. Next is using lookup tables. Lookup table, that is LUT, is the faster way to compute the hit or miss transformation when structuring elements are small. The lookup table is constructed by using function makeLut based on a user supplied function. Function applyLut processes binary images using this lookup table. The line of code persistent space LUT used in function endpoints establishes a variable called LUT and declares it to be persistent. MATLAB remembers the value of persistent values in between function calls. The first time function endpoints is called variable. LUT is initialized automatically to the empty matrix. When LUT is empty, the function calls makelet, passing it a handle to subfunction. Function applylet then finds the endpoints using the lookup table. The lookup table is saved in persistent variable LUT so that the next time endpoints is called, the lookup table does not need to be recomputed. Next is function bwmorph. Toolbox function bwmorph implements a variety of morphological operations based on combinations of dilations, erosions, and lookup table operations. Its calling syntax is G equals to bwmorph f, operation, n, where f is an input binary image, operation is a string specifying the desired operation, and n is a positive integer specifying the number of times the operation should be repeated. If argument n is omitted, the operation is performed once. The two main operations are thinning and skeletonization. Thinning means reducing binary objects or shapes in an image to strokes whose width is 1 pixel. Skeletonization is another way to reduce the binary image objects to a set of thin strokes that retain important information about the shape of the original objects. Skeletonization and thinning often produce short extraneous spurs called parasitic components. The process of cleaning up or removing these spurs is called pruning. Next topic is labeling connected components. The term connected component was defined in terms of path, which is turn depends on adjacency. All the connected components in a binary image are computed by using bwlabel function, which is having a syntax as L, num in square bracket equals to bwlabel of f, con, where f is an input binary image and con specifies the desired connectivity. Its value is either 4 or 8. Output L is called a label matrix and num, which is optional, gives the total number of connected components found. If parameter con is omitted, its value by default is given as 8. Next is morphological reconstruction. Reconstruction is a morphological transformation involving two images and a structuring element instead of single image and structuring element. One image, the marker, is the starting point for the transformation. The other image, that is the mask, constrains the transformation. The structuring element used defines connectivity. Toolbox function imreconstruct is used for morphological reconstruction, which is having a syntax as out equals to imreconstruct marker, mask. In this, the first operation is opening. In morphological opening, erosion typically removes small objects and subsequent dilation tends to restore the shape of the objects that remain. However, the accuracy of this restoration depends on the similarity between the shapes and the structuring element. But opening by reconstruction restores the original shapes of the objects that remain after erosion as well. Because both opening and opening by reconstruction have erosion in common, the first step is to erode an image using imerode function, which is having the syntax as f equals to imerode of f. Finally, reconstruction is obtained by using syntax fobr equals to imreconstruct fe, f. Next point is filling holes. Morphological reconstruction has a broad spectrum of practical applications, each characterized by the selection of marker and mask images. Toolbox function imfill performs this computation automatically when the optional argument holes is used, having syntax as g equals to imfill f, holes. Next is clearing border objects. Another useful application of reconstruction is removing objects that touch the border of an image. Again, the key task is to select the appropriate marker to achieve the desired effect. Toolbox function imClearBorder performs this entire procedure automatically. its syntax is G equals to I am clear border f comma con, where f is the input image and G is the result. The value of con can be either 4 or 8. This function suppresses structures that are lighter than their surroundings and that are connected to the image border. So this is all in this chapter. Thanks.